Number 26, or sorry, number 27, 28, and 29 are all part of the same roadmap, so I'm going to go over them in one video. So let's start with figuring out let's start by figuring out what X looks like. So we were told that following treatment with a Gilman reagent and an acetal protecting group, we're left with this. Now, we have to go backwards, so let's look at this first step. When you see a diol with H+, you should automatically think acetal protecting group. And you see that right here, your ortho-base, right? We have a little snowman with an arm. Now, going backwards, all you have to do is erase the two carbon-oxygen bonds of the diol, and there's your diol right there. And now, remember, the diol, what does it react with? It only reacts with aldehydes and ketones, which are carbon-oxygen double bonds. So you just need to put a double bond O there. And so what we have before that very step is this. A 6-member ring with a carbonyl, and then this group over here. The next thing to point out is, what is this over the arrow? This is called the Gilman reagent, where you see in parentheses some carbon chain, in this case a carbon-carbon double bond. There are two of them in that parentheses, and then you have CuLi. And the only time where we have ever gone over this reaction is in the context of a Michael addition, where you take a carbon, where you have a carbonyl and then an alpha-beta double bond. And then the Gilman reagent attaches there, and through resonance you get O-. And then so if this was like a CH3 from that Gilman, you'd end up getting O- with the carbon-carbon double bond there, and then the CH3 being added on that carbon that it attacked. And then through tautomerization, this would become a carbonyl, a double bond O neutral. So that would be what you expect. And we have something akin to that here. If you notice, the carbon that gets attacked is 1, 2, 3 away from the carbonyl. 1, 2, 3. Oh, hey, look, on carbon 3, we have a carbon-carbon double bond. That must be where this got added. So before that, what had to be there was a double bond between 2 and 3. So the structure of X was a carbon-carbon double bond between 2 and 3. So this right here is your structure for X. Because again, what would happen is this would get attached there, and this would become a single bond because it would first resonate, you'd get an enolate, which then tautomerizes to the carbonyl form. So here's our X. Now, what is next? So we are told that we take this structure over here, we do a fun ozonolysis reaction, O3, and then after that we treat it with NADH4. We didn't actually have to know this step because I think they drew out the product for you, and they said that it was this. Why is this the product? Because what ozonolysis does is it takes a carbon-carbon double bond and splits it in half and makes each end of that double bond into a separate carbonyl. And then NADH4, we don't really care about this because, well, this got chopped off, but we have this, and then NADH4 will reduce that carbonyl into an OH. Again, I don't think they're really bringing that back this semester, so don't worry about O3. Know what NADH4 does, though. It's a weak-producing agent. Now, we are told that we are going to take this, react it with structure Y, pyridine, which pyridine is just a base. That's all you need to know about pyridine. It's a base. And then after that, step 2, H3O positive. And so what I expect to get after that, though, is the structure that they give you. A 6-member ring with a carbonyl. One bond off of that is a carbon, one bond off of that is an oxygen, which is connected to a carbonyl and an OET. So my goal is to have, well, to figure this out, start by comparing what's the same. The 6-member ring is the same, and remember how you remove a protecting group is H3O positive, so this carbonyl must be from that carbon over there. And so this carbon and this carbon, let's say this is 1 and 2, here's 1 and 2. So the oxygen over here has to be doing something, and it has to be connecting to a carbonyl with an OET. So at the very least, we know that structure Y has to have two things in it, a carbonyl and an OET. because those are there and there's no reason they should just magically appear if we don't start with them. But what can we put on this carbonyl that would make this OH want to attack it? Well, a good leaving group. So you have a couple options. You could put a second OET, because if that OH attacks there, this would swing up, and one of those two OETs would get kicked out. That is one possible answer, and it's not listed on the answer key, but I think that would still get full credit. Another option is give an even better leaving group than an OET. Make it a chlorine. Chlorine is an even better leaving group than OET, so when this is attacked and this swings up, when it swings down, between the option of kicking out a Cl- and an O-, Cl- is much more stable, so the chlorine would always be the one to get kicked out. So structure Y has two possibilities in my opinion. Either an ester with two of the same OET groups, or an ester with a Cl on it. Either way, this oxygen will get deprotonated by the pyridine. O- will then attack here. This will swing up, form an O-. That O- will swing back down to reform its double bond and kick one of these leaving groups out, either the OET in this structure or the Cl in this structure. So there's our structure for Y. So now we have this. So now we have this, and we're reacting it with two sets of arrows. First set of arrows is NaOET, step 1, step 2, H+, and then after that we're doing another arrow where we treat that with step 1, LDA, a bulky base, and then step 2, CH3I. The temperature they list with the LDA step doesn't really matter that much. At least for your purposes it doesn't. Okay, so let's start with that first arrow. NaOET with H+. What will that do? Okay, I see it. So what that NaOET will do is it has two possibilities. The OET could attack here. This would swing up, swing back down, and kick the OET out again, and then nothing would happen after that, so that doesn't make sense. And if it kicks this group out, well, we're kind of back to square one, so that's not going to happen either. At least it shouldn't. The only other option is NaOET minus is going to, the OET minus is going to act like a base. So I have to ask, where is the best spot to deprotonate? Well, there's no alpha protons of this carbonyl, there's an oxygen over there. And if it's not an alpha carbon to a double bond O, this carbon doesn't really have any acidic protons on it, even though it's a single bond away from that oxygen, because it's not a double bond O. So the only option, the only alpha proton I have are this one and this one. Now, if you looked at my explanation for the Robinson annulation in number, I think it was 26, yeah, 26, you saw that this hydrogen is generally not the one you pick, because you'd end up forming a ring where the bridgeheads are really, really far apart. You have a 1, 2, 3, 4, 5, 6, 7-membered ring in this example. So 1, 7-membered rings are bad, and 2, you'd have a bridgehead that's 1, 2, 3 apart. 1, 2, 3, 4 apart, which is really just not nice because the rings will kind of fold in on themselves. So this hydrogen is much better to pull off because it'll make a 1, 2, 3, 4, 5-membered ring. So that NaOET, what it will do is it's going to deprotonate this hydrogen, make your enolate, and you get O- on a 6-membered ring, carbon-carbon double bond, 1, 2, O, OET. And now this will swing back down, and this this carbon-carbon double bond will use its electrons to attack the carbonyl, and this will swing up to the oxygen. And so I would have double bond reformed on the 6-member ring, carbon attached to here, which we said we're making a 1, 2, 3, 4, 5-membered ring, so I'm just going to draw a 5-membered ring now. Now let's say this is 1, 2, 3, 4, 5. Okay, so here's 1 and 2, because those are part of the 6-membered ring to begin with. 1 connected to the carbonyl carbon, so that's now an O- and an OET. And so that's 5. 4 was actually an oxygen, so I need that to be an oxygen. And 3 had nothing special, he's just there. Okay, and now an O- will swing down and kick the OET out like usual. And so now you have a carbonyl, a 6-membered ring on that that carbonyl is on a 6-membered ring, a 5-membered ring coming off of that with an oxygen in it, and a carbonyl there. So this would be the intermediate you get after the first arrow. Now what's the second arrow going to do? You're treating it with LDA, a bulky base. So you're going to look to deprotonate from where the least substituted hydrogen is. You have this hydrogen over here, and you have this hydrogen over here. Now this hydrogen is cluttered among a bunch of things, the carbons, the oxygens, and so it's kind of sterically hindered, and LDA being a bulky base probably wouldn't want to grab that. This hydrogen, where there are two, it's much more easy to grab because it's on the side, it's not stuck in the middle, and there are more of them to begin with. LDA, being a bulky base, will always look to pull off the proton from the less substituted side, the side with more hydrogens. And so you're going to form your enolate over there. And so now you would have you would end up getting the 6-membered ring, the 5-membered ring with the oxygen in it, 1 carbonyl, 1 O minus because you formed your enolate there. Now your final step over that arrow is CH3I. Treat that with CH3I. And so what's going to happen is the O minus will swing down, the carbon-carbon double bond will use its electrons to attack the CH3, and iodine, being a good leaving group, will be kicked out. And so the final product, the structure of Z that we're trying to figure out, would look like this. The 6-member ring is still the same because we didn't mess around with that. The 5-member ring coming off of that, we're done reacting with that, so that's not changing either. This O minus swung back down to reform its double bond O, and it used the electrons of its enolate double bond to attach a methyl there. So this right here is your structure for Z. Okay? Now there was one bonus question to this, number 30, which said, okay, so now you have this fun-looking thing, and we're going to give you a really, really scary-looking molecule and ask you, well, what were the reagents, or what was the name of the reaction that helped you get there? So this was a bonus, and so they made it intentionally scary-looking, but let's try and figure it out. So I'm going to redraw Z in a second, and then we'll figure it out.